All right, Matt 2, we got lesson 2.3.1, day 1, conditions for similarity. There's already stuff written down here because I started to do this lesson, and then there was an announcement over the all call, and it just ruined it, and I accidentally deleted it. Anyways, there were problems. Anyways, so we're going to do conditions for similarities. So Erica wants to help deciding if they have two triangles, if they're similar or not. So here's the two triangles that Erica's looking at, and we want to help her decide, are these triangles going to be similar or are they not similar? All right. So what must be true for the sides and angles if they are going to be similar? And we say that the sides would be proportional. Proportional sides means that if you compare the corresponding sides between the two triangles, that the ratio or the fraction of those corresponding sides should reduce to the same number. The sides won't be congruent to each other, but they'll have the same scale factor. But the angles are going to be congruent to each other. So we're going to use a protractor, which is what we use to measure angles, and a ruler to show that the sides are proportional and the angles are congruent to each other. All right, so first thing that I'm going to do is look at the angles, because the angles are supposed to be congruent. So with a protractor, when you put it down, you're going to put this center part at the vertex of the angle, and then this line down here, you're going to try to measure up the line with the line of the triangle. So it's not the most exact thing possible, but is that the center? This looks like it's 110 degrees. So I'm starting at 0, going all the way around. I just moved it, sorry. Going all the way around, that's about 110 degrees right there. So I'm going to say that this angle is 110-ish. Again, it's not going to be perfect. I'm going to measure all the other angles. Okay, so this angle over here, I'm measuring from the other side, so it's going to be slightly different. All right, I think that's about it. It looks about 30 degrees to me, somewhere around 30 degrees. Okay, so we're going to call this one 30 degrees. Then I'm going to measure this final angle over here. It's hard from where I'm sitting. All right, so this one's going to be, well, we'll call it 40 degrees right there. Now, if you're doing this yourself, you would want to double check that all of these add up to what? Yeah, 180, because the triangle sum theorem. And the way that I did it, yes, they do add up to 180. Awesome. So that's the, I don't know if this is the original or the copy. She didn't tell us. So anyways, we're just going to move on. Over here, this angle right there is a little bit off. Looks like almost 109, but we're going to just call it 110. It's pretty much there. Maybe like half a degree off or something like that. But I'm just going to call it 110, and we're going to pretend like everything's fine. Other one, measure this angle over here. Yep, that's 30 degrees. So just like the last one is 30, got the reflection. That's nice. 30 degrees. And the other one, I'm not going to waste time measuring it. It's got to be 40 because 110, 30, this one has to be 40 degrees. All right, so all those angles are congruent, which is what we want. We want the angles to be congruent to each other. Now the sides are supposed to be proportional to each other. So I'm going to take out, I'm going to do centimeters. And again, not super exact, but I'm going to call that, what am I going to call it? So measuring out my centimeters, that's going to be 8 point, let's call that 8.7. 8.7 centimeters. All right, 8.7. Next side, we're going to call 11.5. And this side, oh man, that's 15 right there. So let me measure the last part. 15, 16.5. All right, so this is going to be 16.5. All right, so there's the big one. Let's measure the small one. So I'm going to measure the small one. real close here. Can't tell if that's 5.1 or 5.2. Want to split the difference? We'll call it 5.1. 5.1. I bet this is really entertaining to watch. This is probably the most boring stuff you've ever seen. Anyways, I probably should have just told you I measured it and told you what I got, but it is what it is. We're going to just finish. 6.8. So it's just like you were in class with me, enjoying watching me use a ruler. I'm going to call that 9.8. Yeah, it's almost 9.9, but I'm going to call it 9.8. Okay, so obviously these aren't super exact measurements. We've already shown that all the angles are congruent. That is actually good enough, but we're going to move on and pretend like it's not. So I'm going to find the ratio that all of these should be reducing to. So I'm going to compare 9.8 over 16.5. Okay, so those two correspond to each other because they're both between the 40 degree and 30 degree. Then 5.1 should correspond to 8.7. So I'm going to look at that one. 5.1 compared to 8.7. Then over here, 6.8 corresponds to 11.5. All right, I'm going to pull out my calculator and find out what those come out to. I'm going to pause so you don't have to watch me doing this. All right, so I finished using my calculator and working on this, and they all came out to approximately 0.59. Now, they were not exact. Like this one was a little bit over 0.59, this one was a little bit over 0.58, but darn it, that's really, really close. This is what we call proportional because they're all reducing to the same fraction here. So if I'm going from this one to this one, it's a reduction. And the scale factor would be 0.59. So it's smaller than 1. That's why it's a reduction on that one. So it looks like all the angles are congruent and all the sides are proportional, meaning that when I compare the corresponding parts, I get the same ratio each time. Okay, so the last thing that it asked us to do was to see if there's a point of dilation. Now remember when you do a dilation that wherever the point of dilation is, it goes through the two corresponding angles. So if I were to do a point of dilation for this next one, the point of dilation should go directly between these two endpoints over here. So I'm going to draw a line over to here somewhere, just off into the distance. So there's my line, and I kind of screwed it up. It's all right. It's been a long day. There we go. So that line goes off into the distance. Now I'm going to do it from this one over here. So if there is a dilation, oh, that wasn't very good. You get the point. So anyways, so if it's the dilation there, it should radiate out from the point of dilation. And then finally, here's my last one. I should have got a longer ruler, but I didn't, so we're just going to move forward. There, I'm going to keep on making the line go farther out here. And look what we have here. They all meet. That's the point of dilation. So what I have here is when I've connected all the vertices from the corresponding angles, we all head back to the same point, which would be our point of dilation for the shape. So is this shape similar? Yeah, it's pretty darn similar. The angles were congruent to each other, the sides were proportional, and we could even follow out from each vertice back all the way to the point that it was dilated from, because dilations make similar triangles. Yay. All right. Now, what we were showing there on that last part is for triangles to be similar, that all of the angles had to be congruent and all the sides had to be proportional. So we have to prove all three angles congruent, all three sides proportional, But just like proving triangle congruence, there are shortcuts where you don't have to prove all 6 things, all 3 angles, all 3 sides. So our first shortcut is called angle-angle similarity. In angle-angle similarity, if we can prove 2 of the angles are congruent, then those triangles have to be similar. So let's look at this one right here. So I've got this shape right here. I've got a triangle. It's been dilated with a scale factor of 4. How can we prove that those angles are congruent? Well, here's how. I can tell that this line here is parallel to this line here. They're parallel. They're both vertical lines. Now, since these are vertical lines, these become transversals. And then using corresponding angles, these 2 angles would have to be corresponding angles because this is on the interior, this is on the exterior. They're both on the same side of the transversal. Corresponding angles are congruent when the lines are parallel. And then down here, using this transversal, these 2 angles would be corresponding angles. Because the lines are parallel, one's exterior, one's interior, they're on the same side of transversal, those are corresponding angles. And there goes the light because I haven't moved around enough. And there it is again. I hate doing these videos after school. This always happens. All right. Anyways, I now have 2 angles that are congruent to each other. That is enough to prove those 2 triangles are similar. Just having the 2 angles. Now, there's a reason why we only need the 2 angles. And the reason is, if 2 of the angles are congruent, since they always add up to 180 degrees, the third angle is always going to be adding up to, the third angle is always going to be congruent. If the 2 angles are congruent, then the third one's going to be congruent too, because they're going to add up to 180 degrees every time. So yes, we have enough information to prove those 2 triangles are congruent by angle-angle. If you have 2 angles, we know nothing about the sides. I mean, we could measure them, but we don't know anything about the sides. We don't have to. If we know the angles are congruent, then the triangles are going to be similar to each other no matter what. Scott thinks these 2 triangles are similar to each other. All right, Scott. Let's see if you're right or not. Okay, so I know that this angle is 68 and this angle is 87. Okay, so 68 plus 87, how much does that add up to? That adds up to 165. 68 and 87? Yeah, that's 165. If I subtract, let me double check that. It's the end of the day. I need to make sure I'm right. So if I take 68 plus 87, 155. See, I was off. End of the day. Yeah, don't believe your brain. So we subtract 180 from it. That last angle has to be 25 degrees using triangle sum theorem. Over here, I've got 87 plus 25. That comes out to 112. Subtract it from 180. 68 degrees. Are those 2 triangles congruent? Yeah. Scott, I think you're right. So because we've got this angle here is 87 and this angle here is 87. So those angles correspond to each other. Then we've got this angle here at 68 and we've got this angle at 68. They correspond to each other. We don't need the third angle, but if we needed it, it would definitely still be 25 and 25. So once 2 of the angles are congruent, really the third angles are congruent. So it's called angle-angle, but once you have 2 angles, you have all 3 angles. So how can we tell if all the angles are congruent? Well, we use the triangle sum theorem. And we solve for the missing angles. Why do we only need to prove 2 pairs of angles are congruent? Because if 2 are congruent, the third angles automatically are congruent. And that's actually its own theorem. It's called the third angles theorem. And it makes sense because it has to add up to 180. So if two of the angles are the same, then the third angles have to be the same too because they're going to add up to 180. All right, so angle again says that if we can prove the angles are congruent, you don't need to know anything about the sides. Nothing at all. That's enough to assume right away these two triangles are similar to each other. Okay, next shortcut. Side angle side. So this is different from side angle side when we're proving congruence. Remember with side angle side, the corresponding sides have to be congruent. But in similarity, the corresponding sides have to be proportional. They have to reduce to the same scale factor. So what we're going to do is we're going to double the length of the sides on either side of the 20-degree angle. Okay, so here's my 20-degree angle, and I'm going to double the length. Let's use centimeters, they're better. Hate to say that as an American, but it's true. All right, so this one is 6 units long, 6 centimeters long. So I'm going to extend this and double it, and I'm going to extend it out to 12. Okay, so this is the original. The original was 6, but then the new shape is 12 because I'm doubling the size. I'm going to do the same thing with the bottom one. Bottom one is 7.5. All right, so if I double 7.5, that would be 15. So I'm going to extend this out to 15. A good thing that barely fits on my ruler. All right, there's my new triangle. So this side over here was 7.5. And then the whole thing was 15. All right, so you're looking at these two triangles. They have the same angle. This is the reflexive property. So the reflexive property doesn't only work with sides, it also works with angles. So if you've got a shared angle, it's just like the shared sides that we did with congruent triangles, they're still going to be congruent to each other. So what I have here is here's one side. The original was 6, the copy was 12. Remember, you usually do copy over original. So looking at the copy was 12, the original was 6. That reduces to 2. So that's a side. Then we had the reflexive property. And then we have the other side. The copy is 15. The original is 7.5. 7.5 or 15 over 7.5 is still 2. So I've got side, angle, side. And both the sides reduce to the exact same scale factor of 2. So that means they're proportional to each other. So since they have proportional sides here and a congruent angle in between, this would be side, angle, side. Now that is enough to prove those two triangles are similar to each other. Just knowing that I've got a side and another side over here that's proportional, and then the angle in between. Now I could take out my ruler at this point and prove to you, that if we measured this one, that it would be half the size of that one, so they would be proportional if I did that. We can now also know that this angle here is congruent to that one there, because corresponding parts of, or corresponding angles of similar triangles would be congruent to each other. Now, I never measured that, but I don't have to, because this is one of my shortcuts. I've got side, angle, side similarity, so now I know automatically that that angle is the same as that angle. I also now know automatically that this angle is the same as this angle without measuring it, because just having proportional sides with an angle in the middle is enough to prove the triangles are going to be similar to each other. The end. All right, we will take this up again with 2.3.1 day 2 on the next video. All right, bye-bye.